We are now led to a discussion about turning points. And a turning point on the graph of a polynomial is anywhere where the graph is changing direction. So notice that here the graph is going down, down, down. It hits this, and then it's going up, 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 up. And then we hit a turning point, and we turn and start going down. And we continue to go down until we hit another turning point where the function now switches to going up. And then when I say changing direction, and in anything that I'm talking about with these polynomial functions as we are moving along the graph, it's important to note that we're always moving from left to right because the x-axis does have an ordering to it. We read it the same way that we read a book, from left to right. So every time we hit a turning point, we are either hitting a local maximum, like right there, or a local minimum right there. Basically the hills and the valleys of the graph. And there's a theorem that tells us that a polynomial with a degree n can have as many as most as n minus 1 turning points. So for example, if I have a polynomial of degree 5, the largest number of turning points that it could possibly have is 4. The theorem also states that if you're looking at the graph of a polynomial and you see n minus 1 turning points, however many turning points you see, it means that the degree of the polynomial is at least one more. So if I'm looking at a polynomial and I see 3 turning points, for instance, like here, I see 1, 2, 3 turning points, it means that the degree of this polynomial is at least 4. So because this graph has 3 turning points, it could be degree 4, 5, 6, 7, so on and so forth. Now, I hope you would think, well, this definitely can't be degree 5 because of conversations that we had during our previous lecture. Just looking at the end behavior of this, both ends of that graph shoot up. So I definitely know that this polynomial is of even degree. But I digress. So let's look at an example now. I want to write a polynomial who fits the graph that we have here. So we're going to begin by focusing in on the x-intercepts. This polynomial has x-intercepts at -2, 0, 0, 0, and 2, 0. And we know that each x-intercept is going to correspond to a factor. I can also see that this polynomial has 3 turning points. And the theorem that I have summarized above that we just talked about implies that this is at least degree 4. We can also see that the graph is touching the x-axis at the x-intercept of -2, 0. And so we definitely know that the 0 of -2 has an even multiplicity. We were told to use the smallest degree possible. So when I start writing this polynomial function, I'm going to give the 0 of -2, which would correspond to the factor of x plus 2. I will be giving that multiplicity 2. I gave that multiplicity 2 because it is touching there. However, when we get to the 0 of 0, the x-intercept is 0, 0, which would just give us a factor of x, it crosses through, so I'm going to leave that with a multiplicity of 1. It also crosses through when it gets to the x-intercept of 2, 0, which would correspond to the factor of x minus 2. And so I will leave that with a multiplicity of 1. Notice I did leave a space right here. I'm going to come back and talk about that, but I just want to make sure we're clear on how I am using these x-intercepts to determine what my zeros are. And then from my zeros, I turn each 0 into a factor. Some factors have multiplicity 2. Because I can see that at that 0, at that x-intercept, the graph touched the x-axis instead of crossed through it. Okay, so now that that's cleared up, the reason why I left this question mark in the front is because I don't necessarily know what this leading coefficient is of this polynomial, right? It could be any number and it would not change the zeros of the graph. So to help us determine it, I'm going to use this point -1, 6 that we have not yet used. We didn't use it because we haven't needed it thus far because it is not a 0, right? So that point of -1, 6 would not help us build out these factors. Just for aesthetic purposes, I'm going to rewrite this with the x in the front because I think it looks a little weird with the x tucked in the middle. And we all know that multiplication is commutative, so it doesn't matter what order we write our factors in. So now let's use the fact that this function goes through the point -1, 6, which means that when we plug -1 into the function, when I go in and replace x with -1, we get that this is all equal to a positive 6. That is what that means. So now let's simplify this. So on the left side here, I have a 3a equal to 6, which implies that a is equal to 2. And so now we know that the equation of this polynomial is 2x multiplied by x plus 2 squared multiplied by x minus 2. Leads us to our next try it, where you will be doing a very similar process on the graph that is given here. So as a quick summary of what we know so far about polynomials, we know how they generally look. We know when looking at a polynomial how to determine its degree. We find the y-intercept by plugging 0 into the function. Every term with an x would disappear and only leave us with our constant term for the y-intercept. We learned that the graph of polynomial functions are both smooth and continuous. If we have a degree n polynomial, it can have no more than n-1 turning points. This is not written in factored form, right? Like this is not written in factors like this. It's written in standard form. But if it is written in factored form, we can see what the multiplicities are. And we know that if the multiplicity is even, the graph will be touching the x-axis at that x-intercept. And if the multiplicity is odd, the graph will be crossing the x-axis at that x-intercept. Okay, that's too much. There we go. Between zeros, the graph is either entirely above or entirely below the x-axis, and we've already talked about end behavior of these polynomial functions, which we can determine by looking at the simpler power function that is the leading term of the polynomial. Finally, for our last example, we are going to put together all of the knowledge we have about polynomials so far in order for us to analyze the graph of this polynomial, which is really what this entire course is about. We want to be able to analyze both polynomial and rational functions. Now, if you'll notice so far in this series of videos for today, I have not used Desmos. I have not used the calculator. I have not used the graphing calculator. There's going to be lots and lots of things that we do in this course that you could argue, well, why can't we just use a calculator? Theoretically, you could, but that's not what we're here for, right? So I would like to teach you how to do analysis without a calculator. Some things we will need to use a calculator for, and when we need them, we will use them, but let's not focus on that. So first thing I want to do to analyze the graph of this polynomial is I want to determine the end behavior. In order to know the end behavior, we need the leading term of this polynomial. This is not written in standard form. It's not all multiplied out, but we could still determine the leading term by taking the leading term of each factor. So what I mean by that here, this first factor is 2x. Its leading term, the first factor is 2x plus 1. Its leading term is 2x. The second and final factor is x minus 3 squared. Its leading term would be x squared. Putting those together would give us 2x cubed. So we know our leading term is 2x cubed. I see that positive 2 in the front and the odd 3 as the degree, which tells me that the graph has the same end behavior as x cubed, which means that as x goes off to negative infinity, as we go off to the left, the function is shooting down to negative infinity. And as x goes off to positive infinity, as we go off to the right, the function is shooting up to positive infinity. Now we want to move on to find x-intercepts. We find x-intercepts by setting the function equal to 0. And now that we have the function set equal to 0, I will apply the zero product property and set each one of these factors equal to 0 to see that my two x-intercepts are at -1/2 and a positive 3. So our x-intercepts are the points -1/2, 0, and 3, 0. Now to find our y-intercept, we find our y-intercept by plugging 0 into the function. So I will be replacing all of the x's in the function with 0, which leaves us with 1 times 9. And so this function has a y-intercept at the point 0, 9. Now we will move on and make a little table that consists of the zeros, their multiplicity, and then we will use the parity of that multiplicity. Parity means even or odd, to determine whether the graph will be touching or crossing the x-axis at those x-intercepts. So we only had 2 zeros because we only had 2 x-intercepts. They were -1/2 and +3. The multiplicity of -1/2 depends on the exponent that we see on the factor 2x plus 1. Has an exponent of 1 on it, which is odd, so I know that the graph will be crossing through the x-axis at the x-intercept of -1/2, 0. And then finally, our 0 of 3 came from the factor of x minus 3 squared, because that squared gives us a multiplicity of 2, which is even, which tells me that the graph is going to touch the x-axis at the x-intercept of 3, 0. Our second to last step, we want to determine the maximum number of turning points. That is always equal to the degree of the polynomial minus 1. In this case, the degree of the polynomial is 3. And we know the degree is 3 because, remember, we did determine what the leading term of this polynomial was. And we should be able to see the degree in the leading term. So 3 minus 1 gives us 2. So this graph can have no more than 2 turning points. And now finally, we want to put all of this information together in order for us to be able to graph this polynomial function. So I'm going to start off by setting up my x and my y axes and labeling both of them. I'm going to go by 1s on both of my axes. Well, not on both of them, because I think our y-intercept was up at 9. Yeah, our y-intercept was up at 9, so I'll go by 10s on my y-axis. Yeah, that'll be fine. Okay, so what information do we have? We know we have an x-intercept at -1/2, 0, and we know we have an x-intercept at 3, 0, and a y-intercept at 0, 9. We also know the end behavior was that the left end of the graph shot down. So I am going to start from the bottom down here on the left side as I come in and approach that 0. I also know that the right end of the graph shoots up. I'll deal with that as we continue to work our way through. So coming in from the left side, just this piece right here is using the end behavior. I'm going to come in, get that x-intercept. Now what should we be doing at -1/2? We should be crossing the x-axis. So we're going to cross through the x-axis and go hit our y-intercept at the point 0, 9. But then we're going to need to be turning around because we need to be able to hit this x-intercept at 3. Now when we hit the x-intercept at 3, we should only be touching the x-axis, so I'm going to need to turn back around, and I'm going to continue to go up. And I know that I'm going to continue to go up because I'm going back to the end behavior that tells me that the right side of the graph shot up. And so now you all are going to mimic these 5 steps to analyze the graph of this polynomial function to submit as your final try it.